Alright, so welcome back. We're going to be talking about taking the derivative in sort of a different way. We're going to be talking about what's called implicit differentiation. And so far, even though our functions can look really bad because you can have really bad products or you can have really bad chains, our functions are really nice in the following sense. They've already been solved for y in terms of x. So you have functions like y equals x squared, or y equals x cubed, or y equals sine of x, or things like that. It's always y equals something. But what if I gave you an expression that it was hard to get just in terms of y, or just in terms of x, and you actually kind of had to leave it the way it was and try to work with it from there? You know, for example, I gave you x squared y squared equals x sine y, or e to the y equals y minus x, or so on. Right? These are hard functions because you can't isolate one of the variables very easily. And so what would we do? How would we be able to take the derivative and find the slope of the curve that these make? Well, do you remember that we have a lot of different notations for the derivative? That we can use y prime, or f prime, or d dx of f of x, or dx of f of x, and we have all these different notations. Well, we also learned the chain rule. For example, what if I wanted to take the derivative of f of x cubed? Well, we treat f of x like it's a variable, like x, and the derivative of x cubed is normally 3x squared, so we get 3f of x squared, times the derivative of f of x. But that's like y cubed prime. And that's like 3y squared y prime. And so this notation, using y instead of f of x, and remembering that y is just some function of x, is going to help us figure out the derivatives by using this notation. And so the derivative of y cubed uses the chain rule, since y is a function of x. So another example. Suppose I wanted to take the derivative of sine of 3y. Well, it's just cosine of 3y times the derivative of 3y. Well, the derivative of 3y is just 3 times the derivative of y, which we write y prime. How about the derivative of e to the y squared minus x squared? Well, the derivative of e to the anything is just e to the anything times the derivative of the thing that's up in the exponent. Well, how do we take the derivative of y squared minus x squared? Well, we need to take the derivative of the two parts separately. The derivative of x squared is easy, that's just 2x, and the derivative of y squared is 2y dy dx, which we write as 2y y prime. And so the derivative of e to the y squared minus x squared is just e to the y squared minus x squared times 2y y prime minus 2x. And we have to do this anytime y is a function of x because dy dx is asking how y changes when x does. And so you can think of d dx of x squared as using the chain rule, but when we do that, it would just be x squared dx dx, it would be 2x dx dx, and dx dx is just 1. And that's usually silly to write. We don't usually write those, because we know how x changes when x changes, 1 to 1. So here's a nice example. Here's something we're going to do. It's actually going to produce a result, and we're going to take this circle, which has that equation, and we're going to ask, what would happen if we wanted to put a tangent line at that blue point on the circle? Right? We would need the slope, and how could we figure out the slope? Well, we have an equation, and so we can take the derivative of both sides of this equation. Right? If these two things are equal, then the derivatives should be equal. And so we're going to take the derivative of the left side and the derivative of the right side. The derivative of the left side, well, the derivative of x minus 2 squared is 2 times x minus 2 times the derivative of x, and the derivative of y squared is 2y prime. The derivative of 4 is 0 because 4 is a constant. Now, since we want to find the slope and y is a function of x, we need to find y prime, right? Y prime tells us the slope. So we need to get y prime by itself. That's actually not too hard. X prime is just 1, and so we get 2x minus 4 plus 2y prime equals 0. We can move everything away from y prime to solve for it. So we get 2y prime equals 4 minus 2x, and then we divide by 2y, and we get that y prime equals 4 minus 2x over 2y. So now let's take a point. The point that I have on that circle is 3 comma negative radical 3. So if I plug in 3 for x and negative radical 3 for y, what I'm going to get is I'm going to get the value of y prime. And so I'm going to do that, and then I'm going to simplify, and it turns into radical 3 over 3. So radical 3 over 3 is the slope of the tangent line there. Let's take another random equation. We have sine of xy equals 1. This is a terrible looking equation, but let's talk about what we could say about it. Well, it's important to know that the derivative tells us about the slope of the tangent lines. So let's take a derivative and see what we can find about the slopes of the tangent lines. Well, the derivative of sine of xy would have to equal the derivative of 1. Since those two are equal to begin with, their derivatives would be equal. Well, the derivative of sine of xy is just cosine of xy times the derivative of xy. The derivative of 1 is just 0. So how do we take the derivative of xy? Well, we use the product rule. X times the derivative of y plus y times the derivative of x. Well, that gives us xy prime plus y. Now, in order to get y prime by itself, we have to multiply through by cosine xy, and then move y cosine xy to the other side, and divide by x cosine xy. Now that just equals negative y over x as long as cosine of xy is not 0. If cosine of xy is 0, then the derivative is undefined, because we'd have 0 over 0. So let's go ahead and look at one of the points on sine xy equals 1, right? So if you let x be 1/2 and y be pi, sine of pi over 2 is 1. So that is a point on sine of xy equals 1. So the slope of the tangent line is given by negative y over x, which is negative pi divided by 1/2. And that simplifies to negative 2 pi. So we can write an equation for that, and if we plug in 1/2 and pi for our y and x values, we get y minus pi equals 2 pi equals negative 2 pi times x minus 1/2, which gives us the equation y equals negative 2 pi x. Okay, so here's a neat application of implicit differentiation. We can take the derivative of the inverse. So if you have f of x as a function, and you let y equal f inverse of x, well, the definition of y equals f inverse of x would be that x equals f of y. So if we take the derivative of both sides of x equals f of y, what we get is that 1 is f prime of y times dy dx, or 1 equals f prime of y times y prime, which when you solve for y prime gives you 1 over f prime of y. Well, what was y again? Y was f inverse of x, right? So we can replace y with f inverse of x, and now we can get y prime just in terms of f inverse, and x. Y prime is just 1 over f prime of f inverse of x. So here's a rule. You should know it, and you should use it, because it helps you take the derivative of inverse functions. So let's practice it on something we know. If we restrict the parabola f of x equals x squared to just values of x greater than or equal to 0, then we have an inverse, and that inverse is square root of x. Well, let's take the derivative of the square root of x using the inverse derivative rule. It's just 1 over f prime of f inverse of x. Well, f prime of x squared, right, is 2x. And so f prime of f inverse of x is 2 times f inverse of x, which is just radical x, so that's 2 radical x. And so x prime is just 1 over 2 radical x. And we knew that already, right? The derivative of the square root of x is 1 over 2 radical x. And so the implicit way of taking the inverse derivative, that works out to be exactly what we expected for this one function. Now, we should ask ourselves, why does this rule make sense? And if you look at the graph of the two functions, and you go over to a point, say 4, 2 on radical x, and 2, 4 to x squared, right? The slopes are going to be 1 over each other. Why? Look at those two lines, the bright red and the bright blue. Those two lines are reflected over the line y equals x. So they're the images of each other over that reflection. Well, the slope of one of those is going to be 1 over the slope of the other one. And the point on the blue line is going to be the inverse of the point on the red line. And so that's why we have to do f inverse of x, and then we compute f1 over f prime evaluated there. And so that's it. That's everything you need to know about implicit differentiation and the inverse derivative rule. So go ahead, do the homework, and I'll see you next video.